Okay, we're reviewing what went on in the test, and question number 1 was an issue, and we're just going to go back there real quickly to look at that. Why is cobalt placed before nickel? And cobalt has to come before nickel because nickel has more protons, and that's what determines the atomic number. Okay, let's go on. Number 5 was the next one that was troublesome. And in this chart, what you have to do is think about one very important thing. Is this looking familiar? Yeah. Okay. This guy is our electronegativity, which is also our ionization energy and the trend. So, where do we get the very lowest ionization energy? Alkali earth, which is the guy, or the alkalis, I'm sorry, the alkali metals. Where are they? Come on. Where are the family elements? Okay, alkali family, that's what they're asking about. So the alkali family has got to be down here where it has the very lowest electronegativity or ionization potential. Okay, the trends are the same. They're not the same thing, but they are the same trend. And so if you look at this W right here, that guy is got to be something like lithium. Okay, if you look at lithium on the chart, he'll be on the periodic chart. We're looking at this row right here, and lithium will be at the top of that row, or column, not row, column. So this column is the alkali earth, and the letter that has to be that is the ones that have the very lowest ionization energy. So how do you get the lowest ionization energy? You look at this guy, and that gives you the way to figure that out. Lowest ionization energy is right in the bottom left-hand corner of the little chart that or the trend chart that I just drew. And if you look at this arrow right here, that arrow gets smaller as we go to the left. And so anywhere in this column, we would have our lowest ionization energies, which is what you see with W. Ionization energy is the very lowest for all of the elements that they've listed here, or that they're representing with the W's. Okay, trends are just that. They're trends. They're not precise. As you can see, this guy here is a little bit higher than this one, which is not according to the trend. But the trend gets us to the right part of the chart. Am I making sense here? Yeah. Okay. That's how to do this one. Okay, let's see if we can extend this. What do we get if we're talking about X's? What column do you think that might be? Highest ionization energy. Fluoride. Fluoride, yeah. Fluoride's the dude. This guy here would be fluoride, most likely. And this might be anywhere from bromine down to aspartame. Okay, that's column 7 or 17, depending on what your chart is numbered with. Okay. So, get the idea of how to do a deal like this? Yeah. Has to do with the first ionization energy. Why is the ionization energy lower for the alkalis? Because think about their electron configuration. How many electrons in the outer shell in column 1? 1. Okay. If we take away 1 electron, what do they look like? Huh? No, what do they look like? What kind of element do they look like when we take away 1 electron from column 1, guys? Noble gases. Yes, the noble gases. So they're happy to be noble gases. In fact, they're as happy as a pig in slop. And you might notice that I have pigs and slop on my YouTube favorites. And you can see pigs and slop. They're very happy. Very, very happy. Slop is their food. Yeah. Okay, let's go on. And we'll go to number 8. How do you guys feel about this one? That was pretty easy, wasn't it? Yeah, okay. You just go by the column number. So that tells you the valence electrons. And here we go on number 8. Now, think of this. This is Dalton Thompson. Rutherford. Yeah, Rutherford Mark. Yeah. Okay, so this is the Rutherford dude, right? Gold foil experiment. So, number 8 and number 9 are both the same kind of question. And one of the things you might think about to make this guy make sense, if I set up a virtual wall, and I had in the virtual wall, virtual wall would be on the computer in actually 2D, but you could make it look 3D. So we stand up in front of that virtual wall with a shotgun. Yeah. Okay. And we just blast that wall. Well, all the buckshot goes through the wall, except 2. See, right here. 2 out of every 100. 2 out of every 100 aren't going to go straight through. About roughly 2% of them, 1 in 100, will go through with a little bit of deflection, which means if this is the nucleus, the alpha particle is coming like this, off like that. Deflection. Remember the theater in the round? Okay, the alpha particle source is here, and it's shooting its little alpha particles down to the gold foil, and some of the hits, or most of the hits, are going to hit right in direct line. They're mostly going to hit right in here. Okay? However, you get a few hits every once in a while over here and over here. What we're talking about there is the 2%ers. Okay, these guys. But the 0.01%ers, which is 0.001, 1 in 1,000, if I'm shooting at that wall, I better have a nice shield, because 1 out of every 1,000 of those pieces of buckshot is going to come right back at me. Okay? The deflection, instead of being off to the side or even off to here, they're coming right back here. Really big deflections. Okay? Actually, rebounds almost. Okay? What does that indicate? That most of the space in my virtual wall is just that, space. But I have some very tiny, teeny little things that we're going to call nuclei. And those nuclei is what Rutherford discovered, much to his surprise. Okay? So this question and this question are both answered with the same stuff. Same kind of background material. Okay? And then number 10. Why are enormous amounts of energy required to separate a nucleus from its component protons and neutrons into its component protons and neutrons, even though the protons in the nucleus repel each other? Okay, protons repel each other. So why do they stay together in the nucleus? I don't really think anybody knows that for sure. They talk about this thing right here in letter D, the forces holding the nucleus together are stronger than the repulsion forces. Well, duh. They weren't. The nucleus wouldn't hold together, right? They have to be. And you can't see this on the video, but you can certainly see this here. I'm trying to put it together with all the force that I have, and it just doesn't. You couldn't help me enough. Okay? That doesn't go together. I'm trying to put 2 very strong magnets together at North Pole to North Pole, and it just doesn't work. I can't even get right up to it. I can't. There's no way I can touch it, and you can really feel that if you're on the other end of it, and you're holding one, and I've got one. You will definitely feel that. But the forces holding that baby together are so strong that it overcomes the forces that the protons are pushing against each other with. Yes?
So even if you have a small magnet and a big magnet, you'll still do it?
Oh, yes. Yeah, the bigger one of the magnets is, the more it's going to push.
Isn't it just gonna like turn around and go?
Well, yeah, but if that assumes it's a small magnet like the other little magnets I have. Yeah, yeah. You got quite a push there, and if the magnets are held firmly in place by some other force like putting them in a vise or something like that, you would really feel that, and not a whole lot you could do about it if you get the super strong magnets like this. Very powerful. Okay, that's it for this little review.